In this video, I'm going to go over the airframe design for the Roku Super Heavy prototype hexacopter. This is really only the beginning, and if you haven't caught the first video, check it out here. If you like loads of techie detail and want to go full nerd herd with me, subscribe to the channel to see how this all comes together. See you in 27 seconds. My name is Ben Stineman, and I started Rotor Visual back in 2015 to focus on developing and operating commercial unmanned aerial systems, or drones. In late 2019, it felt like it was time to go big, and I began designing a new aircraft capable of lifting pretty much any camera system. So join me on this journey as I document the process of building a massive drone. Alright, before we get into the airframe design, we need to take a quick detour and go over some of the initial decisions I made in order to help better define the envelope or base parameters for designing this frame. The motors and propellers play a massive role in determining the payload capacity and power systems on an aircraft like this. So for this prototype, I decided to select commercially available off-the-shelf motors and not spend months or even years trying to develop and manufacture those from the ground up. I looked into many options available from manufacturers like T-Motor, DJI, and a few others, but ended up going with a power system from Hobbywing intended for large, autonomous, industrial, and agricultural unmanned systems. The Hobbywing X-Rotor Pro X8 is a complete system. The motor with ESC and propeller are all tuned for optimal performance as one unit. A single X8 system can deliver 7 kilograms of thrust at full power and maxes out at over 15 kilograms peak. This puts a hexacopter in the realm of 42 kilograms of thrust at full power. I didn't stutter. 42 kilograms. That's over 90 pounds of thrust. I plan to revisit the details on these motors again in a later video when we take a deeper dive into the power system design. That brings us back to the frame design itself. With the propulsion system selected and locked in, it gave me a set of constraints or guardrails to work within for defining the rest of the airframe geometry. As I mentioned in the previous video, 6 motors really feels like the best balance between redundancy, power, and complexity. So I started with the most popular and frankly most logical shape to facilitate 6 arms for 6 motors, the classic regular hexagon. A regular hexagon has many intriguing mathematical properties like being composed of 6 equilateral triangles as well as having 120-degree internal angles. Since those 6 triangles are equilateral, the long diameter is 2 times the side length. These mathematical properties make it rather easy to calculate the minimum arm length based on propeller diameter. When you visualize the shafts on the motors from the top down, they form the points of a hexagon. As mentioned before, the motor and propeller system I selected for this project has a 76 centimeter diameter propeller, which means the distance between the motor shafts has to be 76 centimeters plus a bit more so the prop tips don't collide. The central hub of the airframe is just another regular hexagon concentric to the hexagon created by the motor shafts. The size of that was determined by a number of factors like the size of the arm mounting brackets, the payload mounting setup, and the avionics devices, as well as how it would fit into a road case. One of the major considerations I wanted to take into account was how this airframe would be torn down or made to be more compact for transport. This gets increasingly difficult as the frame size gets larger, and I found myself looking for options from various road case manufacturers like Pelican, SKB, and others. The desire to use a brand name case is based mainly in the fact that the TSA and airlines are familiar with them, ultimately making the baggage check process easier. The main way to accomplish this is to implement some sort of arm folding mechanism, the end goal being to decrease the airframe footprint for transport. I went through many iterations of thought exercise on arm folding methods and orientations. I evaluated what I refer to as the spider, or a folding style, which typically consists of arm roots that have a hinge mechanism that allows the arm to fold down toward the ground. This type of frame geometry tends to be popular, but it results in the aircraft needing a large, cube-shaped case for transport. The folding method that makes most sense to me is what I refer to as transverse, where the arms fold horizontally against the center hub of the airframe. This keeps the frame flat, allowing it to fit in a case that is potentially less bulky. This decision led to determining the best way to implement the hinge. I experimented briefly with a frame layout that had the arms mounted to the edge of the center frame hub, where the arm root bracket itself was also the hinge mechanism, but that most likely would have required machining and testing the custom brackets. I ended up finding aluminum hinges for carbon fiber tubing from a vendor in China. It not only came in the proper size, but it also had a confidence-inducing locking mechanism. It uses a spring tension bolt with a locking ring. To aid in the arm folding, as well as get the propellers even further from the potential field of view of the camera, in the most common underslung mounting position, I designed a vertical offset bracket to raise the outer motor arm section above the center hub of the frame. This design uses 2mm carbon plate and aluminum tubing clamps to give the outer arm sections a 2-degree upward angle. As far as material selection is concerned, there are really not very many practical options other than carbon fiber and aluminum for balancing the trade-off between rigidity and weight on a flying machine. It may be a bit overkill, but I selected 4mm carbon plate material for the main central hub section. Carbon fiber plate is fairly easy to obtain, but a bit challenging to machine. We'll cover that in a bit. I also debated quite a bit about the arm tubing size. After running the numbers on a few different carbon tube sizes with the decal tool, I made the decision to select 35mm outside diameter carbon tubing with a 32mm inside diameter, giving a wall thickness of 1.5mm. It was readily available and, according to the tool, is over 130% stronger than 30mm OD tubing often used on large multi-rotors. The trade-off, of course, is weight. I'm taking these calculations with a grain of salt, but they are based in known physics formulas for material strength, and going into full finite element analysis or static and dynamic load simulations at this point seems overkill, considering the mass of the aircraft and payloads. Since this is a prototype, I tried to select off-the-shelf hardware as much as possible. I was able to find aluminum CNC parts for the arm root brackets as well as the hinges, as mentioned earlier. The arm root brackets are a fairly straightforward clamping CNC part for 35mm OD tube. They have 6 M4 threaded mounting holes per side. The screws and bolts that were included with the brackets and hinges will likely be replaced with fasteners of known grade and quality where possible. After selecting the root arm brackets, I realized there would be a lot of holes to be drilled in the carbon fiber frame hub plates. A lot. Getting the hole placements to be accurate and clean was not something I was willing to try by hand or even on a manual milling machine. So I modeled the arm roots to use as hole pattern references for modeling the carbon fiber plate parts I needed to machine. The process went pretty smoothly in Fusion 360. I added quite a few additional hole pattern options for internal mounting plates as well as larger holes for external payload adapter plates. I had explored buying the plate stock and finding a place to machine it, or even buying the equipment to machine it myself, but that's a rabbit hole unto itself. However, having used Armatan FPV quadcopter frames, it occurred to me that I had seen their Armatan production site where you can have your own designs machined from carbon fiber. All that was required was to export the 2D sketches of the carbon fiber plate with the hole patterns as DXF files, and Armatan took care of the rest, like creating G-code for their CNC process and taking care of all the setup, etc. The parts came in about 2 weeks and the quality is amazing. The mass of the frame is obviously a very important parameter to monitor when selecting and designing components for an aircraft. I've been tracking that in a table and the frame is currently weighing in at around 5 kilograms on paper. I'm optimistic that this will not be too far off once the frame is actually built, but we will have to see how that pans out in the build video. As you can probably tell, there are hundreds of considerations to take into account while designing an airframe like this. I know I've likely overlooked something critical, but again, this is a prototype. I accept the responsibility of having to make a modification to the design on the fly, or even having to get a part remade. But this is so much fun to me. I love it. In the next video, I will be going over the avionics and power system design and product selection. Again, if you haven't already, consider subscribing to the channel and clicking that bell so you can watch this play out. See you next time.